All right, so think about this. A nuclear reactor sits there for years, just churning out incredible amounts of power. But what happens to the fuel once it's, well, spent? It's one of the biggest questions in nuclear energy. And, France has this really unique answer that kind of flips our whole idea of waste on its head.
So, yeah, what's the deal with this stuff after it comes out of the reactor? I mean, it's intensely radioactive. You might be picturing it getting buried deep underground somewhere and just forgotten, right? But the reality? Oh, it's way more complex and honestly, a lot more fascinating. This is where a pretty incredible journey begins.
And here's the thing that just completely turns that whole idea of nuclear waste upside down. When that fuel comes out of a reactor, it's not mostly waste, not even close. A whopping 96% of it is actually stuff we can use again. We're talking uranium and plutonium. It's only that tiny little 4% slice that's the real high-level waste, things like fission products. And this one fact, this is the key to understanding everything France does. It's all about recycling. Okay, so the first leg of this epic journey is actually getting the fuel from the power plant to the recycling facility. And let me tell you, this isn't like your average Amazon delivery. This is a super meticulous, high-security operation. First, they load the fuel assemblies into these absolutely enormous specialized containers called casks. Now, most of the trip is done by rail, and then a truck takes over for just the last few miles to get it to the Oriano facility at La Hague. And you better believe, every single step is monitored, every move is planned down to the second. And just to give you a sense of the scale we're talking about here, one of these transport casks weighs 110 tons. That's heavier than a blue whale. It's insane. But that crazy weight isn't just for looks. It's a super critical part of the whole safety system. Seriously, each cask is basically a fortress on wheels. They are engineered and tested to survive just about any catastrophe you can imagine. A high-speed crash, a massive fire, even being dropped deep underwater. The whole point is to make absolutely sure that no matter what happens, the stuff inside stays sealed and safe. So, once that mobile fortress arrives safely at the Le Hague facility, the spent fuel is ready for the next phase. And it's time for what I like to call the Big Blue Cool Down. We're talking about a long, supervised chill-out session in some of the most impressive swimming pools on the planet. Okay, picture this. The cask is moved over one of these massive pools. Then, using robotic arms, because you're not getting close to this stuff, the fuel assemblies are unloaded completely underwater. From there, they're placed into these big storage baskets at the bottom of the pools, which, by the way, are over 9 meters deep. The water here is just such a simple but totally brilliant solution. It does two critical things. First, it's a coolant. These fuel assemblies are still putting out a ton of heat. In fact, all the pools together give off enough heat to power about 10,000 boiling kettles at once. Wild, right? And second, that 9 meters of water is the perfect natural shield. It blocks the intense radiation, which means it's actually safe for workers to be nearby. And, like the folks at Orano say, this isn't just about waiting around. It's a strategic pause. Storing the fuel like this lets the most intense, short-lived radioactivity just fizzle out naturally over a few years. That makes the fuel a whole lot safer to handle for the next step, which is the really crucial part, unlocking all that potential locked inside. All right, so after cooling off for about 3 to 5 years, the fuel is finally ready for the main event. This is where the magic happens. It's time for the real recycling, using a super advanced chemical process to separate the good stuff from the actual waste. So they take the assemblies out of the pools, chop them up into little pieces, and dissolve them in nitric acid. Yeah, you heard that right. This creates a kind of radioactive liquid cocktail. Then, this amazing process called Purex kicks in. It's a really sophisticated chemical trick where they use a special solvent to pull out just the uranium and plutonium, leaving all the other nasty radioactive bits behind. And this is the result, the big transformation. Let's say you start with 1,000 kilograms of so-called spent fuel. After you run it through this process, what do you get? You get 960 kilograms of perfectly good uranium and plutonium, ready to be made into new fuel. And the actual high-level waste? Just 40 kilograms. I mean, that is a massive reduction. It shrinks the final waste footprint down to almost nothing and lets us power reactors all over again. That's what we call closing the fuel loop. But what about that last 4%? I mean, this is the really, really radioactive stuff, and we need to make sure it's locked away from the environment for like thousands of years. The solution they came up with is actually pretty elegant, and it's super robust. They turn it into solid glass.
So that leftover liquid waste from the Purex process, it gets piped into a furnace and mixed directly with molten glass. The process is called vitrification, and it's brilliant. It basically traps the radioactive atoms inside the chemical structure of the glass itself. They're not going anywhere.
And we are not talking about some arts and crafts glass blowing here. This whole thing happens at over 1100 degrees Celsius. It all goes down in a remotely operated, heavily shielded facility. Once it's ready, this molten, radioactive glass is poured into stainless steel canisters where it cools down and becomes solid. The final product is a 400-kilogram canister filled with this solid, black, almost obsidian-like glass. And inside that glass, the most radioactive elements are locked away for good. They can't dissolve in water, they're incredibly stable, just totally secure. These canisters are then stored safely in ventilated pits that are shielded with tons of concrete.
I mean, this whole closed-loop system of using and reusing fuel is pretty impressive, right? But it obviously requires some serious long-term planning. So what's the game plan for the next 100 years or so? How are they going to manage all this material?
Well, the strategy is broken down into a few phases, because you got to plan decades ahead for this stuff. Right now, the existing pools have enough space for about the next 10 years. Then, around 2025, they're starting a densification project, basically using new storage rocks to cram about 30% more fuel into the same pools. But looking way down the road, past 2030, the plan is to build a brand new centralized storage pool that's designed to last for 100 years. This makes sure there's always a safe place for fuel to wait its turn for recycling. So at the end of the day, France's whole approach dramatically shrinks the amount of final waste. It turns what most people see as a liability into a valuable asset. But that vitrified glass, as stable as it is still going to be radioactive for a very long time. And that brings us to the ultimate question, the one everyone in this field is grappling with. What's the final move in this long, long chess game against radioactive decay? What is a truly permanent solution? What does forever actually look like?